Hello guys, good morning. You are welcome to my YouTube channel, the Explicit Tutorials. As you all know, I'm Mr. Joseph or Mr. Explicit. And please, as you watch this video, do subscribe so that when I upload new content, you would be notified by YouTube, alright? So in today's class, we are going to be discussing capacitor and resistors. Capacitors and dielectric and resistors, okay? Now, what is a capacitor? A capacitor is just a device or an instrument used to store electric charges. Do you understand? A capacitor is just a device or an instrument used to store electric charges. Do you understand? Then the ability of the capacitor to store electric charges is called the capacitance of what? The capacitor. Capacitor stores electric charges. Good. The ability of this capacitor to store electric charges is called the capacitance of what? The capacitor. Alright? And please take note that the fundamental unit or the basic or standard unit of electric charges is in coulomb. Alright? According to the law of electrostatics. Alright, so we'll get to that. That like charges repel, unlike charges what? Attract. That the force of attraction or repulsion between two charges Q1, Q2, alright, is direct proportional to their products and inversely to the square of the distance separating the two charges apart. Don't worry, as time progresses, we are going to be discussing electric field. Okay. Now, from what we've done already, so the capacitance of a capacitor is affected by different factors. All right, we'll say factors affecting the capacitance of what? A capacitor. Big letter C is used to denote the capacitance of a capacitor. One, the nature of the material. The nature of the material, that is, we refer to the thickness of the material. All right, then two, the area of overlapping, of the overlapping plates. And we'll say area, don't forget it is measured in meters. The formula is meter what? Squared, because it's area times breadth. Alright, meter squared. Then three, the distance between the dielectric. Alright, the distance between dielectrics or plates. The distance between the dielectrics or what? Plates. Alright. Now four, the distance between the dielectrics. Sometimes they will give you permittivity. Okay, permittivity is noted as E naught. All right, that is epsilon what? Naught. Now these are the factors affecting the capacitance of what? A capacitor. And the capacitance of a capacitor is directly proportional to the area and inversely toward the distance. All right. Now, in order for me to eliminate this sign, I'll be having capacitance equal to E naught, then area over what? D. Do you understand? It therefore means that from this formula, the capacitance of the capacitor is directly proportional to the area and inversely proportional to what? The distance between the plates. All right, meaning that as the area is increased, the capacitance of the capacitor increases. As the distance increases, the capacitance of the capacitor decreases, because they have inverse relationship. All right, any theory you hear inverse, it means that as one increases, the other one decreases, as the case will be. Number five, the position of the material. The position of the material or plate It means that when the position of the material is what? Separated. Alright, the capacitance of the capacitor what? Decreases. So please take note that the capacitance of the capacitor is equal to E naught times area over what? D, which is the distance. Don't forget that the area is meter squared, and the distance is what? Meter. It's in meters. But area is what? Meter squared. So that is for that. Excuse me. So these are the factors affecting the capacitance of a capacitor. Okay. When we now talk of the work done, all right. We'll talk. Let me bring in the charge where we have Q equals to what? CV. All right. This Q here represents electric what? Charge. And C represents the capacitance of the capacitor. Alright, then V means the potential difference. Potential difference. We commonly use P dot D, and potential difference is measured in volts. Alright, V is measured in what? Volts. Okay, and you should know that voltage simply means the potential difference between 2 points. Voltage means the potential difference between 2 points, and of course it's measured in what? Volts. Don't forget what I just illustrated. All right, it is very, very important. And the work done in a capacitor, is equals to E1 over QV. Alright, the work done in a capacitor is equal to 1 over 2 QV. And don't forget that Q is what? CV. I have 1 over 2 CV times what? V. And this becomes 1 over 2 CV squared. Alright, so please, when you hear calculate the work done, you bring your mind to this formula. I believe what I've just done is clear enough. Alright, the next thing we are to do is to look at capacitors in series and parallel. Capacitors in series and parallel. Capacitors in series and parallel. Alright, capacitors in series and parallel, which means that when a capacitor or when capacitors are in series, they are shown as so I'll call this C1, C2, C what? 3. Alright, so we have 3 capacitors. Now the equivalent capacitance, alright, the equivalent what capacitance when you have when you have more than 2 capacitors occurring in series, it becomes the inverse. So the inverse of what? Each capacitor. Alright, the inverse of what? Each capacitor. And you should also note that when you have only 2 capacitors, alright, now the equivalence or total capacitance, alright, is equal to their products divided by their sum. Alright, when you have more than 2 capacitors occurring in series, you use this. But when you have just 2, or when you have exactly 2 capacitors in series, alright, you use their products, which is C1 times C2 over C1 plus C2. Their product divided by their sum. That is how it is. It is very, very simple. But when you now have when you now have when you now have capacitors in parallel, when you have capacitors in parallel, so the total capacitance is simply the sum of the individual capacitors, C1 plus C2 plus what? C3. It's as easy as that, which means that in parallel capacitors, in parallel capacitor, the equivalent capacitance is bigger or higher than the sum of the individual what? Capacitor. But capacitors in series is less than the sum of the individual what? Capacitor, because here we are having what? The reciprocal of the total capacitance. You should also note that in series, the charge is equal to the sum of the individual charge. That's Q1 plus Q2 plus what? Q3. It's as easy as that, okay? So these are the things you must know in capacitors in series and capacitors in parallel, okay? So this is the first part you must understand fully. Now let us look at some past questions. It is very important we use past questions to check what we have stated so far. I pray I say it on time. Okay, this one is resistivity. Oh God. I think we should continue. Maybe in our next class, I'll be compiling questions on what we just did. All right, let us continue with the class. Now we now have resistors. Resistors are materials that bring about the opposition to the free flow of electric charges. To resist something means to oppose or to prevent or to impede. All right, so resistors are materials that bring about the opposition to the flow of what? Electric charges. Then the ability of a resistor to oppose the free flow of electric charges, we call it resistivity. All right, resistivity. And resistivity, we have the formula as RA over what? L. All right. So if I want to make resistance the subject formula, I'll have, so this times this is L equal to what? R what? A. All right. So I'll divide both sides by A. So resistivity is a product of the resistor times the area over what? Length. What about resistance becomes what? P, that is resistivity, L over what? A. All right. It means that the resistance of a resistor is directly proportional to the length and inversely to the area. Is that understood? Now, the resistance of a resistor is directly proportional to the length and inversely to what? The area. Unlike the capacitance of a capacitor, which is directly proportional to the area, all right, then inverse proportional to what? The distance. All right, so don't take this for this. Capacitance directly proportional to area. Resistance inversely to what? The area. Take note of that. So I have a question here. I think I saw it just now when I was looking for a question to give you guys. So they said, okay. Oh God. Now they said the resistivity of a resistor is given as dash. The resistivity of a resistor is given as dash. Option A, they gave arrow equal to PL over A. Option B, they gave arrow equal to PM over A. Option C, they gave arrow equal to PA over L. Then D, none of the above. None of the above. You can observe how close option A and C are. Of course, this is not there. Alright, the resistance of a resistor is given as resistivity times length divided by what? Area. So option A becomes a right answer to this question. I believe you are following up, right? So please follow just be following. Make sure you give it your full attention, okay? Once I'm done with the class, I will also look at some past questions, even if they are not related to the topic we are treating right now, okay? Now, we now have resistors in series. Resistors in series. We have arrow 1, arrow 2, and arrow 3. Alright, resistors in series is equivalent to resistors in parallel. Do you understand? Sorry? Resistors in series is equivalent to capacitors in parallel. That is what it is. Because series resistors, the effective resistance is simply the summation of the individual resistor. Alright? Is equal to the summation of the individual what? Resistor. But don't forget that in capacitance we said that the equivalent capacitance is the reciprocal of what? The individual capacitor. That is 1 over C1 plus 1 over C2 plus 1 over C3. Alright, so that is for that. Then we now have our resistors in parallel. Resistors in parallel. Resistors in parallel is arrow 1, arrow 2, arrow 3. Alright, so the effective resistance in parallel when you have more than 2 resistors, it's 1 over arrow T equal to 1 over arrow 1 plus 1 over arrow 2 plus 1 over what? Arrow 3. Alright, but when you have just 2 resistors in parallel, alright, so arrow 1, arrow 2, alright, so the effective resistance, alright, is equal to arrow T, then the products of the resistors divided by their sum. Alright, it's as easy as that. Very, very simple. Yeah, it is very, very easy. It is not a big deal. It is very, very easy, okay? Don't forget that from this stuff, please take note that in resistors in series, alright, the same current flows through them, alright? Resistors in series, don't forget that we have that Q equals what? IT, and V is equals what? I arrow. I think let me even state Ohm's law. Yeah, Ohm's law. Ohm's law, alright? Ohm's law. And please don't forget that ohms, resistors is in ohm. All right, resistors is in ohm. Ohm's law states that the electric current, are you listening? The board is very small, so let me just say it orally. Ohm's law states that the electric current that flows through a metallic conductor is directly proportional to the potential difference between its ends or across its ends. I say it again. Ohm's law states that the electric current that flows through a metallic conductor is directly proportional to the potential difference between its ends, all right, between its ends, provided that the temperature is kept constant, and other physical properties Ohm's law states that the electric current that flows through a metallic conductor is directly proportional to the potential difference between or across its ends, provided that the temperature and other physical quantities are kept constant. That is Ohm's law. That is, we're having to be V equal to what? I arrow. V equals I arrow. Alright? You can observe that the current is directly proportional to what? V. Alright, if I want to make algebraic formula, I'll now be having divide both sides by arrow. So I'll have current. Current becomes V over what? Arrow. Alright? And don't forget that I, which is current, is measured in what? Ampere. That is big letter what? A. Alright? And the instrument used to measure the amount of current is called ammeter. Alright? The instrument used to measure the amount of an electric current is called what? Ammeter. Alright? But the instrument used to measure potential difference is called potentiometer. Alright? Potentiometer. Alright? Alright, please take note of that. But the instrument used to measure potential difference of voltage, let me use the word voltage. The instrument used to measure voltage is called voltmeter. Voltmeter. As easy as these things, they are past questions and you are likely to see them on the day of your exam. They are very, very easy. Alright, so the instrument used to detect small electric charges, not just to detect, as well as what? The direction of these electric charges. The instrument used to detect the presence and direction of small electric charges is called what? Galvanometer. Galvanometer is a device used to detect the presence and direction of small electric current. Galvanometer. Alright, please take note of that. Now, when we talk of galvanometer, we said that galvanometer is a device that is used for detecting the presence and direction of small electric charges. Now, you should note that galvanometer can be converted to what? Ammeter. Alright, galvanometer is converted to what? Ammeter. And please, for a galvanometer to be converted to ammeter, alright, a low resistance shunt in parallel is used. That's the key word. For a galvanometer to be converted to ammeter, a low resistance shunt in parallel is what used. That is for that. But for a galvanometer to be converted to voltmeter, all right, a high resistance multiplier in series is used. Do you understand? For a galvanometer to be converted to ammeter, a low resistance shunt in parallel is used. For a galvanometer to be converted to voltmeter, it means that the high resistance multiplier in series is what used, meaning that the ammeter is always has low resistance, low what resistance. Please take note of that. Based on this ammeter, now the PD, the potential difference across the shunt, listen, the potential difference across the shunt is equals to the shunt. Let me rub off this one since we have done it already. It's equals to the shunt current times the shunt resistance. Are you listening? The potential difference across the shunt is equal to the shunt current times the shunt what? Resistance. Now, the potential difference across the galvanometer, all right, is equal to the galvanometer current, all right, times the galvanometer resistance. All right, so that is for the first approach. Now, the potential difference across the shunt is equal to the shunt current times the shunt what? Resistance. The potential difference across the galvanometer is equal to the galvanometer current times the galvanometer what? Resistance. That means that what we have here is what? The PD across the shunt. Then you have shunt current. Now the shunt current is given as I minus Ig minus Ig. That's for the shunt current. Then times what? Okay, that is shunt current. Let me write here shunt resistance equal to what? Arrow. Do you understand? Then the next one is what? Galvanometer current, which is given as Ig. You now have galvanometer resistance, which is what? Small letter arrow. Okay, now we are going to equate this and this. We are going to equate these two guys. All right, that's what it means. Now, we don't forget that this shunt current, we have this times resistance, which means I minus G times arrow equal to, we are equating this and this. So we are equating this, everything that we have here, this first one, that is, we are equating the PD across the shunt, which is this, and the PD across the galvanometer. So this one is what we have now. Then for the galvanometer, we are having Ig times what? Arrow. Ig times what? Arrow. So I'll now, from what I have now, what will I do? I can divide through, all right? Because I want to make this to stand alone. So I'll be having because something is missing here. This I, it has to be what included. Okay. Now, from what I have now, I'll now say divide both sides by 1 minus G over 1 minus what? G, such that this will go into this. That is, we are making the resistance shunt to stand alone now. So equal to Ig times arrow over I minus what? Ig. Don't forget this formula. This is for what? Ammeter. Very, very important. Just follow it step by step. You would understand it to the fullest. Okay? You would understand it to the fullest. What about what's it called now? To voltmeter. All right. So it means the potential difference across the voltmeter. We use big letter V. That is V1 equal to Ig times what? Arrow. All right. The current of the voltmeter times what? The resistance. That is, then the PD across the galvanometer is equals Ig times what? Arrow. All right. So we are going to equate this and this. Before we do the equation, V, please, this one is V1 and this one becomes what? V2, right? So V equal to V1 plus what? V2. Right, so V equal to V1 is what? Ig arrow plus V2 is what? Ig arrow. Alright, so V is equal. You can observe that this, something is similar, is common here. So I have Ig, open bracket. Okay, before I do that, let me do it like this. I want to make this guy to stand alone. Alright, so this one we have to cross. It becomes V minus Ig arrow equal to Ig arrow. Right? This one is crossing, becomes minus. Alright, because I'm making arrow stand alone, I'll say divide through by Ig. Alright, so this will go into this. Then arrow becomes V minus Ig arrow over Ig. But this is not simplified enough. I'll do it as arrow equals to V over Ig minus arrow over I what? G. Okay? That is V over Ig minus Ig arrow over what? Ig. So at this one, we cancel out this one. So arrow becomes V over Ig minus this. So it's as very easy. Do you understand? Very easy. It is very important you take note of these formulas. You must take note of these formulas. And please, there's what we call Wheatstone bridge. Wheatstone bridge. Alright, Wheatstone bridge. The Wheatstone bridge is used to measure accurately the resistance of a resistor. The Wheatstone bridge is used to measure the resistance of what? A resistor. The Wheatstone bridge is used to measure the resistance of what? Of a resistor. Now, how do you illustrate the Wheatstone bridge? You have something like this. So here, all All right. So this is arrow 1, arrow 2, arrow 3, then arrow what? 4. All right. And this place is what? The cell, which is what? Electromotive force. All right. So to calculate what we have here, it is simply the ratio of arrow 1. So the ratio, that is ratio of arrow 1 and arrow 2 to the ratio of arrow 3 and what? Arrow 4. Alright, if I should write here A, for example, and B, please note, in case you are given a question that involves diagram, ask you the potential difference between A and B. Please note that the potential difference between A and B is equal to 0. This is position A. Position what? B. The potential difference between position A and position B is equal to what? 0. So potential difference between A and B is equal to what? 0. Please take note of that. Hope it's recording. Yeah, it's recording. Yes, I'm checking. Oh yes, I'm checking, because sometimes it can be very, very frustrating. So please, this is a Wheatstone bridge. All right. We also have what is called the meter bridge. The meter bridge is a form of Wheatstone bridge. It is also used to measure resistance accurately. All right. The formula is R1 over R2 equal to L1 over what? L2. All right. Where L is the length. L1 and L2 are the length. Then R1 and R2 are the resistor. So please take note of that. I don't know if time will permit. So please, at this point, to call it a day. In our subsequent classes, I'm going to be unfolding questions you are likely to see in Physics 102 in general. Thanks for watching. I do have a wonderful day. And please, if you know you have not subscribed, please do so so that when I upload new content, you would be notified by YouTube. I believe you enjoyed today's class. And please, let me give you this as a miscellaneous. All right. Electric field intensity. Electric field intensity is equal to Q over 4 E naught arrow squared. Electric field what? Intensity. But electric potential, all right, is equal to Q over P, that is 4 arrow, all right, not arrow squared. Yes, not arrow squared. So don't take electric field intensity for electric potential. All right, they are both the same. However, this guy does not have what? Arrow, it does not have a square. But if I want to write this in full, I'll be having Q1, I'll be having K, Q1, Q2 over R, that is arrow squared. Alright? But if I want to write it completely, alright, it becomes Q1, Q2 over 4. I've written it in 4. Yes, okay, yes, I was trying to I didn't know that I've already written this here. So in place of this Q, which is the charge, you can put Q1, Q2, and you have the complete equation. Thanks for watching, and do have a wonderful day.